Alright, today we're going to consider the determinant of a covariance matrix. And this hopefully will make the meaning of a determinant a little more clear. Say C is a covariance matrix with the values of 9, 2, 2, 7. We're going to find the determinant of C today. But we know from this that the variance of variable 1 is 9, and the variance of variable 2 is 7, and the covariance is 2. So I'm going to write that here. Variable 1, the variance is equal to 9. Variable 2, the variance is equal to 7, and the covariance we can see is 2. So thus the Pearson product moment correlation coefficient, PPMCC, we know is given by this formula. R equals the covariance over the square root of, we have the variance of one variable times the variance of the other variable there. So we can find this by saying we know that the covariance in this case is 2 divided by 9 times 7. So 2 over the square root of 63, which equals 0.252. We also know from this that the square root of variance is a standard deviation. So for variable 1, the standard deviation is 3. And for variable 2, the standard deviation is the square root of 7, which, by the way, is 2.65 according to my calculations. And standard deviations are like the lengths of vectors for two variables. And the PPMCC, the correlation coefficient, is the cosine of the angle between them. So we can say that the angle, let's do it over here, is equal to arc cosine 0.252, which if I do correctly in my head is about 75.4 degrees or so. So once again, the correlation coefficient is the cosine of the angle between these two vectors, the vectors being length of 3 and 2.65. Now conceptually this might be a little hard, but let's say I drew a vector out here, and let's just assume this is vector of length 3. Okay. Now if we have an angle of 75.4, it's about maybe right here, and we have another vector of length square root of 7, 2.65. And we can connect these if we wanted. So this is actually a large angle, almost as far apart as the vectors could possibly be, which is 90 degrees. So we see that the geometric figure created by these two vectors has a large volume. So this would actually, we can say, has a large volume. Even though it may not look so from my drawing. So the determinant of a covariance matrix gives the generalized variance of that covariance matrix. When the generalized variance is large, the volume of the geometric figure for that set of variables is large. So we can say generalized variance is given by the determinant of a covariance matrix. So in this case, we have C the determinant is going to be 63 minus 4, which is 59, which is the generalized variance. When this is large, the volume of the geometric figure for that set of variables is large. Now I kind of want to step back and just kind of look at this. If you recall from pages 107 to 108 in your text, talks about the Pythagorean theorem, and that's actually how we knew that these standard deviations, 3 and the square root of 7, are the lengths of the vectors for the two variables. Now we'll talk more about, we'll do another example and also find an angle for the new example. So say we have a similar covariance matrix with the same variances, but a much larger covariance. So let's say we had C, we'll call it sub B, and this equals same variances, but the covariance we'll say is 6 this time. So we can find the determinant to be 63 minus 36, which is 27, which is the generalized variance. When the covariance is large, it indicates that the two variances are redundant with one another, so they're overlapping. Thus, the volume, or the generalized variance, will be low. So let's find the the correlation coefficient. So it's going to be R equals our covariance, which is 6, over the square root of 9 times 7, which is the same as what we had before. So 6 over the square root of 63, which equals 0.756. We find the angle here, this is going back to geometry, to be 40.9 degrees. That's if my calculations in my calculator head are correct. So we can draw another figure. We've got the same length because the standard deviations haven't changed because the variance hasn't changed. So this is 3, but our angle is now reduced to 40.9, which, excuse my drawing, but it's about right here, with this vector being the square root of 7. So the angle is 40.9 degrees. So we can see that the generalized variance in the volume is low. So we can say low or smaller volume. And you can see that by my figures, even though obviously they're not drawn to scale, we can see that the volume has gotten smaller. So once again, we see here that the determinant for this matrix is considerably less than the former one. So 27, and the former one was 59. And the former one didn't have that much overlap because the covariance was just 2 as opposed to 6 in this case. We see also that the angle between the two variables in the second covariance matrix is small, meaning that the two vectors are close together, creating a geometric figure with smaller volume. So there's more overlap there. Now I would like to illustrate this further to help y'all understand a little bit more. I mentioned before that up here we had 75.4, which is pretty close to 90 degrees, which would be as far apart as the vectors could possibly be. And the reason why that is, we know that the Pearson product, Pearson product moment correlation coefficient, it's a mouthful, just the correlation coefficient R, is always going to be less than or equal to 1. If it's 1, it's a perfect correlation. So if R equals 1, then the angle will equal 0. So let's say we have a really powerful correlation, but it's not quite 1. R equals 0.99. The angle just using this. You can use your calculator or my head for it. But I'm just kidding, I used the calculator previously. The angle is 8.1 degrees, so it's pretty small. If r is 0.9, the angle actually jumps 25.8. 0.7, the angle is 45.6, so it's getting larger. 0.5, the angle is 60 degrees. Let's say if r is equal to 0.3, the angle is 72.5 degrees. And say it gets really close to 0 and there's almost no correlation at all, the angle is going to get really close to 90 degrees, but it will never reach 90 degrees unless r is 0. So, as covariance increases, so as we went from 2 to 6, our r increases as well. Therefore, the volume decreases, which means we have more overlap and more redundancy. And I just wanted to point that out to you guys, make that connection. As covariance increases, the Pearson product moment correlation coefficient will also increase, and as we see here, it decreases the volume. Okay, you can see by decreasing the angle. Any questions about that? Okay, I hope that helps you understand a little bit more. So, therefore, the determinant is an index of the volume of the geometric figure in an n-dimensional space, where n is the order of the square matrix, in this case 2. Okay, so next let's talk about the trace. The trace is the sum of the diagonal entries of that matrix. Since only square matrices have a diagonal, only square matrices can have a trace. So for example, we can have a matrix E, a 3 by 3 matrix that the value is 4, 5, 1 going across, 5, 9, 2, and 1, 2, 7. The trace of E is going to be the sum of the diagonals, 4, 9, and 7. So 4 plus 9 plus 7 equals 20. That's the trace. Pretty easy, huh? So the trace is a single value, like a determinant, that gives descriptive information about a matrix. It's useful in a covariance matrix, where the diagonals are the variances, so the trace indicates the total number of variance units in that set of variables, or the total variance of that data set. That's what the trace gives you. So the off diagonals tell how much overlap in the variances among the pairs of variables. Like our covariance tells us the overlap, because the covariances are on the off diagonals.